So we will continue to talk about quantification, RNA sequencing. Before we do that, I think just a quick sort of thing about post projects. We are done with mid-sems, and I will still believe that I think we are slightly early for you to think about projects. But I will encourage you to at least come up with broad ideas that you should be doing. We will do one round of submissions about what is a broad idea that you want to work on, and you can do this in um, projects. This will be due for proposals. Like all of this will sound as if this is too much to ask for, but here what we are expecting you to do is I will give you a very quick preview of what the projects looked like last year, and that is by no means the only way to do projects. You should be able to get a hands-on in any problem that you have thought about, right? So at this point, I've not even explored all the technologies that are possible, but that shouldn't prevent you from coming up with a project topic, because uh, broadly, if you can figure out among these areas whether you are interested more in algorithm development, whether you are interested more in doing statistical methods development, you're interested in benchmarking existing methods, you're interested in doing analysis, or anything else which is not covered in these broad topics, you should be able to propose broadly what is the project going to be about. And this week, this time, what I wanted to do slightly differently is rather than showing you multiple different kind of technologies, we will focus on a few of them and go deeper, which is something that I realize that I should be doing because that will pay off in the long run. While the other way that I was initially planning to do is give you a gist of lot of different technologies, I think in the long run that might not stick around, right? So we will have a review of proposals, or a proposal due on next Thursday, which is not this 25th, but 1 week from there. It's a holiday, but hopefully that should still be okay. Where you'll just do a proposal and I'll give you the format for the proposal. It's a very short abstract kind of thing. What is the broad question that you would like to understand? And can you find out data sets against or towards or in that direction for that hypothesis that you have? Should not be very difficult, because we have gone through that exercise, right? When we started this particular, or even the previous hands-on DNA-seq, what we did very briefly is I searched for this on the internet, I got a paper, went on down to that data set and tried to sort of figure out, okay, that this is the data set, let me try to do the analysis on my own. That's kind of the thing that I'm expecting. You have seen a lot of algorithms also, right? Like, so you would be interested about that. If I'm using one algorithm over the other, is it better, right? And at this point, you should be able to sort of figure out or even search what are different algorithms for doing, for example, DNA sequencing alignment. So we use BWA, but there's also something called bowtie. If you want to do benchmarking of them, that's also okay. That's also a valid project to have. So start thinking about it broadly, and I'm happy to discuss, right? So while the group is of 3, but I'm your 4th member, and that's why that's the 3rd member. You're welcome to sort of use me for all sorts of discussion about how you should be doing this project or how you should be sort of taking things forward overall. We will have a short report. This report again is not like 1-pager or 1.5-pager, which will be due in the mid of October, just to see how things are going, right? So that you don't wait till your end sems to actually do the project. I'm letting you know right now that if you start to wait till end semester, this is one of those classes where you cannot pull off a project in the last few days, just because this field requires a lot of actually time, right? So you'll have to start early, even if it means that you're uncomfortable, you don't know what you're doing, that's all okay. You will have to start early. This is one of those projects which unfortunately you'll not be able to pull out on the last night or even the last week. It'll be very, very tough, because you'll run into all sorts of issues. Data wouldn't download, code wouldn't compile, all sorts of things will go wrong. So don't wait till the last minute. Any questions about this slide? Any surprises? No questions, no concerns. Everyone this with me? All good. Okay. Okay. So I'll just quickly show you what sort of project topics were done last time. Let me see if I can make it bigger. Okay, so the first project was a multi-omics framework with protein-protein interaction network analysis for drug repurposing and mpox. Mpox was a big thing. I think this project was a good project to start with. Unfortunately, the data became, so basically what the person wanted to, or what the group wanted to sort of diagnose is how we can use multi-omics, which basically means more than one omics technologies. So transcriptomics, genomics, proteomics, whatever you want to use, for understanding doing protein-protein interaction network analysis for drug repurposing, right? So drug repurposing is a very broad domain, but the idea is that, for example, if you've developed a vaccine for, let's say, one kind of disease, and if you know certain things about this new disease, can you repurpose that particular drug to work on this new mpox, right? So monkeypox, I think now the cases have sort of declined, but this was quite a thing when we actually were doing this project last time. The second one is to analyze hypoxia phenotypes for tumor prognosis. So this is something from a group who was interested in understanding cancer, and people who are interested in cancer would probably understand this. But basically, if there are hypoxic conditions, if your cells lack oxygen, what happens to the growth conditions in cases of how your tumor progresses? That is what this particular project was sort of interested in, right? So I'm sure there will be one disease which you would be able to associate yourself with in some sense, right? Either somebody in your family has it or you're just curious about it. Think of it from that perspective also. That will give you a lot of room for innovation. Then there was ML approach to understand bacteria defense against antimicrobials, right? So actually quite don't remember the details of this project. Let me see. Yeah, we'll come back to this. I don't remember the details of this project. Fourth one was on genome and transcriptome manipulation. So how the kind of stuff that we have done here in course, we were dealing with DNA sequencing data and GTFs, which you'll see today. How to sort of do that manipulation very quickly. I think that was what the tool was about, right? So there was a tool development. This was a tool development kind of a project. Then there was a analysis of mutation signature and CLL, chronic lymphocytic leukemia, with focus on SF3B1 gene. So you can figure out which labs are interested in this, and this was probably from a lab in BSB, who are students from that lab who were interested in understanding this. Then there was bioutils. This was a very, very interesting idea from CS people. I will not go over all the projects, but just to give you some idea. But this was how you can run all these tools from your browser. It actually was very nicely done overall, but I wanted a few more things. Would have liked to see a few more things, but overall, I think this was a very good overall attempt. Let me see if I can highlight a few to give you a flavor. Then there was this one, gene expression data analysis of non-alcoholic fatty liver disease. So kind of data set that we are dealing with, but more generally, they wanted to understand what are the signatures which explain non-alcoholic fatty liver disease. Then there is biomarker discovery for prostate cancer. There is actually this one, sorry, where is it? Yeah, prostate cancer, sorry, it's going up again and again. But there was this one which is also interesting. This came from a math person. They were interested in, they got were not very happy with the FASTQ files size. So they wanted to come up with a better compression scheme of doing lossy compression using quality scores, using machine learning. Good problem, but the solution wasn't as trivial and something which wasn't as polished, but very good idea, very good attempt overall. Then there was again a reanalysis of glioma dataset to get a better understanding of disease pathobiology, sex-specific immune response, and fibrosis mechanisms in tuberculosis, right? So a lot of disease-related stuff, some methods development, and some benchmarking kind of thing. There was one about language models, yeah. Interpreting long range gene regulation with deep learning, cross species analysis using Informer and explainable AI, right? So Informer is a tool which I haven't actually still discussed. At some point it will come up. Is a tool from Google which tries to predict from sequence how the expression would look like in a given context. What they wanted to do was make it work along with cross species. So that was something that they did. So overall, what you have to focus on is whatever question you have, right? As long as you know about, you can search about what are current methods or what are current approaches or what are current data sets that people have looked at. And this should not be a very difficult exercise given that we live in the age of LLMs and of course Google search and fancy search and so on. You should be able to come up with a topic. It shouldn't be that difficult. Any questions? But of course, you're welcome to all come and ask me about if you have broad areas that you still don't know about what you're going to focus on. They can come and please come and talk to me. Sorry, say that again. What is a good? That's a very good question actually. How do you know? How do you distill a project, a broad question into a very specific question, right? So that I'm happy to help you with, right? If you tell me a broad area that you're interested in, we can sort of brainstorm about like what are specific questions in this field which require to be answered. Again, I cannot do a good job with everyone, but some areas I might know something about so that I'm able to. So for example, that cross species thing and some of the other things that you saw were the fourth member, which was me sort of bringing in my inputs, right? So this cross species idea, something as I remember, I think I gave them and so on, but those are things which I'm happy to help with, right? But you'll have to have some baseline upon which I and you can build together. Okay. Any other questions about that project or about projects in general? Okay. If not, we will proceed. And we were talking about how to map data. We had briefly discussed these solutions and we wanted to discuss about pseudo alignment. So today we will finish this and then we'll do the hands-on and we'll come back and try to understand what was happening overall. So the third approach that we had talked about was the approach which is used by this tool called Callisto. Callisto tries to build a De Bruijn graph, and I'll explain in the next slide what is a De Bruijn graph. But imagine you have 3 of these isoforms. These are already annotated in your data. So you know that this particular gene has 3 isoforms, and if you can, this is something you can download from Ensemble or NCBI. Ensemble is the European version of NCBI, but it's run by a different organization. So they have made these isoforms available. Now you can ask me this question that how did we come up with these isoforms to begin with, right? So we have been depositing a lot of RNA sequencing data in public for almost 15 years now. And at each point, you can take that data and you can try to put together that if I try to assemble my transcriptome from scratch, right? So all you get from any RNA sequencing data is these reads. You can try an assembly approach on this. And this assembly approach will tell you that this one maybe came from exon 1 and this came from exon 2, but also had exon 1. And this had exon 1 and exon 3. And this also had exon 1 and exon 3. This will tell you that you can put together an isoform which looks like this, but there's also another isoform which looks like exon 1, exon 2, and exon 3. Right? So that's how these isoforms are developed, and you can download this from the public data sets, from the public databases. So in the case of Callisto, what it tries to do is it creates a De Bruijn graph starting from sequences, right? So those red, those pink, blue, and green are sequences of the exons. Whenever you see a rectangle like this in browsers, genome browser, which I'll talk about in just a bit, this is an exon, this boundary is an intron, and this is an exon again, right? So these are the 3 possible isoforms that you could have got. It creates a De Bruijn graph. What is a De Bruijn graph? The De Bruijn graph is nothing but you take overlaps of k-mers and each node here represents a k-mer, right? So this is k equal to 4. It's a graphical structure, or it's a data structure which is made such that when you take a particular string and you slide your k-mers over each other, each single node corresponds to one k-mer, and it will have an overlap of 3 bases, right? So in this case, AAAG, AAG, these 3 last bases have an overlap. And the reason you're able to do this and use this particular structure is it helps you resolve the ambiguity whether this particular exon came from exon 1, one particular read came from exon or isoform 1 or isoform 2 or isoform 3. How does it do that? So each vertex that you're seeing here is one k-mer. So you take one read and you start to move it along this direction. This is your k-mer representation. So if your read matches up, you're okay to continue. You continue, you found out that the next base also matches, you continue, and you keep going on till you arrive at this location. Now at this location, your read, what the sequence it has a match with this vertex, which means that very likely that read would have been at least this long, because there's no way that it is mapping onto the green location. So you keep continuing on this path and you keep going until the base that you have at the read level matches, right? So you are using this structure to help you guide which potential isoforms did my read come from. There is no alignment at this step, right? There is no Smith-Waterman, there is no Needleman-Wunsch. All you're doing is taking the k-mer from the read, seeing whether this is an exact match or not to some extent. You can allow for a few mismatches, but it's for all other reasons, it's a pure, very simple one match, whether the matching is happening or not. Does that idea make sense? So it is comparing against all the isoforms in the sense that all these isoforms, to begin with, they share the same, at least focus on the blue one, on the pink one and the blue one, right? So if this is exon 1, they have the common exon 1. So that's why they share their entire architecture. Until exon 2 comes in, where in this case it has a shorter exon 2, or maybe this one has exon 3. So it will stop here, because till this point it is sharing all the k-mers possible, which is something which the green one is not, because it got truncated early on, so it has taken a different path. Because the truncation happened here, so the next path, the next exon will have a different sequence, right? So that's why this got derailed in some sense. So at each step, you are taking the k-mer of the read and you're trying to figure out that which of these vertexes is still matching, because that read could have come from any of these exons, any of these isoforms. Does that idea make sense? Right? So what is the problem, right? Like the problem is that my read, I would like to assign a probability that if these are your isoforms A, B, and C, then did this read come from here, or did it come from here, or did it come from A? I would like to be able to assign it probabilistically, and this graphical structure is helping you do that in a much faster fashion because there is no alignment required. So broadly, these class of algorithms are called pseudo alignment. Pseudo because there's no exact alignment that's happening, but you're still doing a k-mer match, and that's where the term pseudo comes from. So since each isoform can share these nodes, if you stop here, right? If you stop here, it can have come from either red or your pink isoform. So these are called compatibility classes. In other words, this read is compatible to both isoform pink and isoform blue, but it is not compatible with isoform green because that has a different structure. So if I take the read and I match my k-mer and I keep going, and if I stop here, the compatibility class of it will be pink and blue because it could have come from either of those. At this point, I've not been able to resolve where did it come from, right? Where did it come from? Okay, so that's the path. For example, given that particular isoform or that particular read, that black read, that you see, you start from here, right? So this is shared, this part is shared in both, at least till this part is shared. This is the read. It's shared between pink, blue, and green. You will travel till here, and here it diverges. But when you take that particular Kamer, you see that it matches the next one. So you keep going here, 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 and you end here, right? This is where sort of your read ends. Now, if you're getting terminated there, then your compatibility class could be either pink or blue. That's what this particular plot shows. Yeah. Each vertex is one Kamer. Yeah, and that's what you're doing in the read as well. So this K is 4 for an example, but your usual K is larger. It's 31 around. Again, that's a magic number in some sense. So you take the 31 Kamer. But your question is again, yeah. Hmm. Hmm. Correct. Correct. No. So each node is a 31 base pair, Kamer. The difference between this node and this node is it shares 30 of them. This shares 30 of them. But at this point, the reason these diverged is because whatever is here, right, that k equal to 1 is not satisfied here. It doesn't share that sequence, so it formed its own path. This still shares k equal to 1, k equal to 30 bases with this vertex, and so does this. But it's a different sequence. It's not the same sequence because you're stopping here, and then you're bringing in this element. So the Kamer changed. Does that make sense? Right? So it's still a 31 Kamer, but this Kamer is different from this Kamer. And the read matches with this Kamer because this came from this Kamer. Okay? So if you were to quantify, right, like if you were to, or other words, think about the compatibility classes, at this point, the read is compatible to either blue, pink, or green. Similar here, this particular vertex, it could have come from any of these isoforms. The moment I took this path, it could definitely would not have come from the green one, and that's why its compatibility class is only pink or blue, and that's what keeps happening here until it goes all the way till here, at which again blue and green become compatible, right? That's happening because their sequence structure is somewhat shared at that angle. So these two share the same Kamer. So each of that Kamer is contained in both of them, and that's why this compatibility class is blue and green. Okay, so the way if you want to sort of count or if you want to quantify which isoform comes from where, you should be able to rather than doing the alignment by jumping from one node to the other, this jump is in some sense redundant because you know that if this is compatible and if this is compatible and this is compatible, it's not giving you any information. So rather than going node by node, how does Callisto, which is a tool that we have been using, how does it work? Is it can jump to unique locations. It can find out that, okay, if this is a new compatibility class, is my read now compatible directly with that node? Because there you have more information. Here information is redundant. It's all blue, green, red. So that's how it saves time because it can skip it. And it saves a lot of runtime. You don't have to move one Kamer by one Kamer. You can actually jump. And that's where the speed comes from. Is that part clear? Okay. So at the end of the running this, right, at the end of Callisto, we will know the likely isoforms the read could have originated from. But how do we actually assign to one or more isoforms, right? So when we created these compatibility class, this read is compatible to A, it's compatible to B, and maybe I will make another structure. So this is, it is compatible to A, again, this and this, right? So overall, this read that you're getting, since there is no isoform here, it is not compatible with isoform C, but it is compatible with isoform A and B. How would we assign them to one or more isoforms? This is the question that I had left you about the puzzle, right? This is the assignment problem. So what is the assignment problem? Initially, assume that your transcript attendance transcript abundance is A, B, or C. This is your isoform, blue, red, or green are your isoforms. Imagine that you have these 5 different reads that are coming, right? So A is a read, B is a read, C is a read, D is a read, and E is a read. Focus on A. This location also tells you where it came from. Okay, so A could have come from blue, or it could have come from green, or it could have come from red. B could have come from B, which is blue, or it could have come from green, but it could not have come from red because there is no overlap. C could have come from blue, could not have come from green, could have come from red. D could not have come from blue because there is no element here. This is a joint read. It could have only come from red. And finally, E could have either come from green or red, right? So if I do quantification, my Callisto algorithm will stop here, right? Will just tell me that, okay, this is what I can best do. But what I want is I want isoform level quantification. I want that how many transcripts are there of blue? Given that you have those reads, is it 2 or is it 3 or is it 4, right? Is it 2? Is it 3 or is it 4? For green, is it 2 or is it 3? For red, is it 2 or maybe 3 or maybe 4? This one is we are confident, right? That cannot go anywhere. D1 is the easiest to tell you that it can only come from red. That you can confidently assign. But the other ones, you're very shaky. You don't know where it came from, right? You don't know where it came from. So that's what we are trying to do. And the way we will do this is by doing a coin toss experiment. And I try to motivate this example in last class when we met before the exams is you have 2 coins and which are A and B, and I haven't told you the probability of getting a heads in each of them, but I want you to be able to guess it, right? So coin A lands with the probability theta A, coin B lands with probability theta B. How will you identify theta B and theta A? So how will you identify theta B and theta A? You have 2 coins with unknown probability of getting heads. How would you solve this problem? Yeah, toss them multiple times and yeah, you'll toss them multiple times and you will count the number of times A gives you heads. When you toss a coin A and B, also you take it and then you toss it, and you're just simply doing what's called MLE, which is maximum likelihood estimation, right? So we don't have to get into the mathematical part of it, but it's basically in the statistical inference literature, this is called as maximum likelihood estimation, which very broadly means that what is the probability at which observing these number of heads that you observed is maximized. That is what your theta MLE estimate is. What is the theta A at which the number of heads that I observed, I have already observed them, at what value of theta A is the probability maximized? That is what your MLE is, right? So based on what is your theta A, you will have, let's say you observed 5 heads and 5 tails, right? So you know intuitively this is at 0.5 is when a probability of observing this is maximized. But had it been 6 heads and 4 tails, intuitively this will be at 0.6. Right? That's what essentially MLE estimate overall tries to do. So this is fair enough, right? This is not a very difficult problem and you can intuitively solve this. But if the problem is now made harder, where I tell you that there are 2 coins, but you cannot, they are identical, as in they are indistinguishable, right? To you, they both appear as just this, there is no label attached to them. And then I want you to be able to tell me that what are the 2 probabilities associated with these 2 coins of getting a heads or getting a tails, or getting a heads for both of them, right? So what is theta A and what is theta B? How would you do this? In this case, whenever you draw, right, you get to draw only these two coins. There is no distinguishability between them, right? So even if I put my hand in a flask, I draw these two coins, I toss it, but whatever one lands with, I cannot tell whether it came from A or B because they are indistinguishable in some sense. But probabilistically, internally, they are both biased by a different bias. There is a theta A and there is a theta B. How would you solve this problem? Is the question clear? It's slightly abstract, but you cannot distinguish them. You cannot see it. You can observe their outcomes, but you cannot see which one is A, which one is B. And I want you to tell me, yeah, you can pick the coin randomly. You don't know whether you pick A or B. You can pick up, yeah, that's a good question. Well, you can choose. There is no observable in the sense that whatever pick you're doing, right, you cannot tell whether it's A or B. Let me put it that way. Hmm. 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 Okay, so you take one coin, fine, and hmm. Mm-hmm. So these are conjoined, let's say. So these are joined in some sense. You have to sort of do the experiments with both of them at once. That's a nice ringtone. What is it called? Okay. Any ideas? Just flash at something in front of you. If I were to tell you that maybe you are allowed to sort of do that experiment that you're talking about, right? Which is you can pick one of them and then try to guess it. Then how would you do it? You just take one of them, toss it multiple times, and then do it, right? But I'm going to make it harder by saying you that um, the probability that you pick each one of them, since it's random, you don't know the identity, right? The moment you pick it, in some sense, you lost the identity of what exactly you picked. Does that make sense? You can do the experiment with one of that coin, but you don't know whether it's A or it's B. Okay. Well, no games. No games. Fair, fair. You know, we are fair people, right? No games, no cheating. No cheating. Yeah. Okay. Okay. So let's think about it, right? So hmm, hmm, hmm. Okay. So see, that's fine. So I think I get what you're saying. So you're saying these are some possibility. Let's try to play this game, right? So say that again. Sum of both the coins. Mm-hmm. Hmm. So you will sum. So you'll take both the coins and you will toss both of them together, and you will count heads. Because if you count heads, that's done, right? There are two possibilities, and yeah. Okay. And then how do you estimate theta A and theta B? Okay, fine. We can play the game. Let's play the game. Okay. So I take this coin, and at this point I am going to cheat a bit, and I do take this coin, and let's say I get this, right? I get 5 heads and 5 tails. right? What does it tell me about theta b? It's fair, right? What about this one? So whatever you're observing, there is some essence of that coin bleeding into your observation, right? For each observation, for example, if I take B again, right? If I take B again and I get, let me make it slightly extreme, right? So 7 heads, 3 tails, this will be 0.7. This is 6 heads, 4 tails, right? So I have sort of moved away from my estimate of 0.5, but every observation will have some component of what was my inherent theta A and theta B, because those are not going to change. So every process that you take from A or B will have to speak for it, right? It will have to sort of tell about what is happening, which choice you made. That is something that you should be able to observe. Now, if you do an experiment like this where the reasons are where you cannot observe, or you cannot observe these labels, you can start with a very simple assumption that at each point theta A and theta B are, whatever, something random. You can start with they are going to be 0.5, right? So we can track these vectors as to what is the number of heads observed using the ith set of tosses. We will calculate the joint probability, right? So this is log of p x z theta, right? What is the z here? The z here is this identity that otherwise you will not be able to actually see, right? So if I gave you only one random coin at each time, you will not be able to assign these labels of A and B. So in other words, that's the hidden variable in this sense, right? You're not actually able to see these values. So that becomes your Z or your Z. We will calculate this joint probability first, which is that, okay, if I were indeed able to observe it, then what will be the probability, right? Which is what example is shown in this case, right? So if I take a blue coin, which is in this case B, then I get 5 heads and 5 tails. Maybe then next coin I take randomly, and the A coin comes, and then I get 9 heads and 1 tails, and that theta A will become, if I keep doing this experiment multiple times for a long range, I will have a tally of A, how many heads does it get, and I will have a tally of coin B. The reason you're doing this experiment again and again is because at each point I actually don't know whether I'm picking A or B. So if I do it 10 times or 15 times or 20 times, I will have some surety that, okay, in these long chain of experiments, I must have picked A and B maybe proportionally equal number of times. Finally, what I will do is I will take this run of experiments. Again, in this case, I'm able to observe A and B. So I can calculate theta A is at 24 by 24 by 6. Theta B is 9 because 9 heads overall and 11 tails, so 0.45. This is fair to do if you could indeed observe A and B, right? Does this idea make sense? Right? You're able to observe A and B. And I'm trying to simulate that, okay, if you are indeed able to observe, this is, for example, what is your maximum likelihood estimate, okay? Okay, right, so that's what this shows. This is just the version of that. And this approach about what do you do if you have missing data, right? What is missing here? The labels that are attached to these coins are missing. This was developed in '88 in a classical paper. This is one of the very, very classical papers. And again, this is one of those algorithms which it works, but when you see it, like, I have no idea how it works, but it works, right? So this is by Dempster et al. This is called expectation maximization algorithm, or maximum likelihood from incomplete data via EM algorithm, developed in 1988. And we'll see, using the same coin toss experiment where the incomplete data is the incompleteness of the labels, how do you estimate what is theta A and theta B? Okay, so once you do have your labels, you can assign a probability about what is the probability that you picked coin A, given that you have made a particular observation, right? So let me first go through that formula, and then let's try to think about how is that formula justified. So E is the observation that you have, right? So you get whatever 5 heads, um, 5 heads and 5 tails in that series of experiments. We can calculate the posterior probability. This is the posterior probability of where it would have come from by this formula, and help me understand why does that formula work. This is the probability that you observed this in 10 coin tosses. What is the probability that this came from A? We have seen these versions of posterior probability when you did the zoonomia example, or when you did, I think, one of your exam questions, where you ask that I've already observed something. So you've observed something. What is the probability that it must have come from some X event or some Z event, given I've already made that observation, and that observation is your I tossed it 5 times or 10 times, and I got 5 heads and 5 tails. Okay, how does that formula come about to be? What are the possibilities of it coming from? What is the probability that this coin is A, given I have made certain observation? How do I solve this? How should I write this? So it's like an engineering problem now, because you know the formula, you have to reverse it. How did it come about to be? How would you write down or simplify this observation, right? What is P of O? How can you observe those 5 heads and 5 tails? I could have chosen coin A, and I would have gotten whatever n number of heads, or how do I finish this? What is the probability, overall probability of observing something like this? 5, whatever the observation is, doesn't matter what it is. But there are a certain number of heads and certain number of tails. Louder, louder, louder. 1 minus theta A. Okay. So I saw H number of heads and T number of tails. Okay. So H plus T is constant, and in this case it's 10. The reason I can make this observation is I take a coin and I get these many heads and I get these many tails if I tossed it with A. But there is nothing so special about A. The overall probability of this is this. Is this fair? Everyone understands? What is the overall probability of observing something? You break it down. It could have, what is this basically, right? It is that you're observing whatever you're observing, law of total probability. Sorry, it's hidden. But let's just probability of observing a full event is equal to probability of observing one event multiplied by the probability of that event itself. And these are A and B are what? What kind of events are A and B? Overall, full on. We don't care about the sequence as such, right? Like we care about the final number of, yes, because that's what informs you about your theta A and theta B, right? Because the sequence can happen in any fashion. Each coin toss is independent, so the sequence does not matter. Okay. Okay. Okay, fair enough. Does that idea make sense, what he said? So whatever I've written is P of A times, so any event can be broken down. This is law of total probability, right? Any event is equal to, what are A and B here actually? What are A and B? What events, in which cases will this hold true? Can they occur together? So they are, there's one more word, huh? Independent, there's one specific word. They are mutually exclusive. If A happens, B cannot happen, right? If B happens, A cannot happen. So the correct version is I should multiply by half, but you'll see it gets cancelled, but that's a good point, right? So at each point, whenever I'm sort of sampling, I'm making the assumption that the probability of sampling A and B are same. They're identical in that fashion, right? And I chose that coin that was identical. That's why 1/2 is a reasonable assumption. You want to make it complicated, you could, that each guess is, so this is, both of them is multiplied by half, right? Probability of observing is equal to probability of observing that observation given A multiplied by PA plus probability of observing A complement, which is that A does not happen and B happens, multiplied by PB. Okay, that's very, very simple law, just simple law of total probability. And okay, so I wrote this down. What is the numerator? Yeah, just the first term, right? So PA given O. So there's a very fancy term for this, Bayesian and so on. There's nothing very, very complicated about Bayesian. For an event A to happen given an observation has happened is equivalent to that both of them happen divided by this event happens. It's as simple as that. Don't have to remember any formula. Okay. Now here, P, A, and O is this, right? What is the probability that A happens and O happens is this. Okay. Everyone with me? And that's where the half gets cancelled. Does that make sense? Very simple, right? Yeah. Yeah. Okay. Anyone wants to respond to that, or anyone has any response? So, forgetting a name. Prabhat. Yeah. Prabhat's question is, I think Prabhat is, you got inspired in the midsem. That's why I see you more often in the. Hopefully, I'll see you more often in the class. Okay, good. One good advantage of having midsem. Okay, yeah. So Prabhat's question is that should you account for NCH, like the probabilities that can happen about the number of points? Say that again. Yeah. So in this case, right, what am I doing overall is you are only tracking. While that is true, like in principle, you would want to sort of take all possible combinations. In this case, your sample size is just determined by what is the overall number of heads. You don't care about what sequence they come in, because that is helping you count the probability of generating a head. So the arrangement itself is immaterial because you're counting the number of heads, right? So your sample space is just a function of what you're counting, and in this case, you're just counting the number of heads. Okay, fair enough. Okay, very simple, right? That's what's called the expectation step. This is the E step of the EM algorithm, right? So in E step, if I do this reaction, or if I do this sort of chain of experiments, and E step, what am I estimating? I'm estimating what is the probability that this would have come from coin A given the observation that I made, right? So let's go back to this table again. That each step, what you're essentially trying to do is you're trying to estimate the number of expectations. So the first, for example, the first guess that you made is theta A is maybe 0.6, theta B is 0.5. It could have been 0.5, 0.5 as well, but in these cases, it's better to start with a slightly differential. It could have been anything, 0.5, 0.6, it doesn't matter. That is your initial random guess estimate. This is what you start from, right? And then you generate these experiments, right? So in 10 different courses, what is it that you get, right? Like at each step, how many number of coins you're getting, right? So at this point, you've lost the identity of each coin toss, but what you get is this observation. Now for each of these observations, you can calculate what is P theta, PZA given this observation. So what is PZA given there are 5 heads and 5 tails? That's 0.45x, that's 0.45 for A and 0.55 for B, again by definition, right? This will have to sum up to 1. And you keep, now at this point, right, if this is true, right, that this observation of 5 heads and 5 tails is essentially made up of 0.45 times A and 0.55 times of B, given that you started with theta A is 0.6, you're doing 10 coin tosses, you can calculate how many number of heads will that generate, right? So overall number of heads that it will generate is 0.6 times 10, or overall number of in this case, the overall number of contributions from each of these A and B will be slightly different, because this number here, right, this number here will be close. Overall, the number of coins, the number of tosses that you're doing are going to be unequivalent for each of them. So at each this step, if indeed A, which has a probability of generating 0.6 heads, is generated, and I'm generating 5 heads, those 5 heads will get distributed differently between A and B, right? So that's why there are 2.2 heads here, because 0.45 of it came from A and 0.55 of it came from B. So that's why that 5 heads got divided as 2.2 and 2.8. Yeah. Yeah. It's random. Yeah, it came from above, right? You know, somebody told you that. This is the first PZ given A. Posterior probability, yes, right? Now at each step, you are making this entire argument probabilistic. You're saying these 5 heads are not 5 heads. This is likely that 2.2 of this came from coin A and 2.8 came from coin B. You repeat this again, right? So now you know how many heads and how many tails are there for A and B. You can now update, go back, and at each step, you can again calculate. If I do this for these 5 or 10 observations, at each step, finally, you will get to 21 heads, right? So at each step, you can break it down, right? Each observation, each row here is nothing but this ratio broken down by what is your observation. For example, in this case, there are 9 heads overall, right? So 7.2 heads, 1.8 heads. Given that your PZA is going to be different because your observation is different. So your 0.8 and 0.2 came from your posterior probability that you use to break down the number of heads and number of tails that you have. You do this 5 times or 10 times or whatever number of times you want to do, and finally go back and calculate how many number of heads you get here. This is the sum of all the heads you get in each of these experiments. It doesn't have to be 5, it could be 6, 7, 10, whatever you choose. How many number of experiments you want to run. Similarly, for coin B, you get 11.7 and 8.4. Now, you can use this 21.3 divided by 21.3 plus 8.6. That gives you theta A is now 0.8, theta B is 0.52. This is your updated belief that having done these 10 experiments and having broken down what is the maximum likelihood of seeing these heads for each A and B, what is my overall estimate? You keep repeating this until this stops to change. which is called the convergence criteria. The convergence criteria is that theta A, theta B that you're deriving at the end of this step, which is called your M step, right? Which is your maximizing. This is where you're estimating the MLE. The final step is nothing but you're literally taking the MLE of this, right? So at this step, you say that if this change, if I run this, keep running this, you can keep running this now, right? Because you have 0.8 and 0.52 now. You will again generate independent set of experiments, keep this loop going on again and again. And at some point, you will see that those numbers don't change across iterations. And that's what your real estimate of theta A and theta B is. Does that make sense? Anyone who's not clear? It's a very beautiful algorithm. It converges. It's guaranteed to converge. There are very, very interesting properties about it, which unfortunately this class will not discuss, but I will upload a paper, I think the Dempster paper. You should go through it if you are interested. What is interesting is it's guaranteed that in each iteration, your overall likelihood is going to be higher than the previous one, but not lower. It's going to keep getting better and better. Right? So what is the beauty of this, right? Like the beauty of this is you knew nothing about these experiments, but with this data, you're able to estimate, right? Just by doing those experiments, you're able to estimate how would it have looked like starting from a very random estimate. Okay? This one is your ZA given theta, this value. So let's do it. 5 heads and 5 tails, right? So PZA given the first observation is nothing but 0. What was your theta A? 0.6. 0.6 to the power 5. 1 minus 0.6 to the power 5 divided by 0.5 to the power 5, 0.5 to the power 5 plus this quantity again. That's what your theta is. You can do this calculation. I'll come up to 0.45. We also do this as an assignment problem, so it will become clear. Okay? That's a good question. In this case of coin toss, 5 to 10. Basically, what you want to do is you want to do slightly more experiments so that this kind of setup is guaranteed where you get to choose both A and B, essentially, right? So you'll do 5, 10, 15 experiments overall, something like that. But in the case of isoforms, you don't actually explicitly have to do an experiment because you've already observed the data. I will show you how it changes when you do the same thing for isoforms. So in this case, you can fix 10 experiments that's what I have observed, and you just live with that. You don't have to repeat the experiments at each point. So this experiment that you're doing, right? These are kind of your reads that you're getting. And this assignment is how you're assigning to that this probably came from isoform 1, this came from isoform 2 and isoform 3. So this experiment of observation, you'll only do it once. It's fixed. But you'll have to have multiple of them, right? You'll have to have at least 10, 15 so that there is enough chance that both A and B get picked up. Otherwise, they might not get picked up at all. Okay? Everything clear on this slide? Okay. So, nothing to do with coin tosses. But what does EM look like in the case of this approach, right? So, in the E step, we calculate the number of reads originating for each isoform. That's your expectation step. And in the M step, which is your maximization step, we re-estimate the abundance of transcripts or isoforms. What is your initial estimate, right? So this is your theta A, theta B. That each isoform is, to begin with, equally likely, right? That's what you're trying to estimate, that what are these numbers, and I don't have any prior, so I'm going to assume that all of these are equally likely. I make this observation. Now this observation is fixed. Yeah. We should do that experiment actually. Yeah, let's do that. We'll have convergence issues. Yeah, we'll have convergence issues. If your experiment goes wrong, not always actually, not always. that's captured in your experiment, right? While you can start with an equal assumption, right? Theta A and theta B are both 5. You'll do this. I will change the assignments. We'll do this particular thing where you will see that if this observation, right? If this captures your A and B, and this has been originated from A and B, it will get automatically adjusted. The only reason you can get unlucky is if this experiment set itself is biased, right? So if in all experiments, if I do 5 heads and 5 tails or 4 heads and 6 tails all the time, then of course there's no way you can resolve it, because this is coming from your real data, right? Like this is not simulated. This is something which you're observed and then you're going back, and it's okay. You can assume that they were all equal. That's correct. So there is no distinguishing between A and B. Yes, you can still not do it, right? Like you'll only be say that, okay, these are the two possibilities. I cannot tell which one is A and which one is B. That is fine, which you're now doing anyway. You're just estimating that, fine, likely there is something about A. The reason this has an identity right now is because of this differential that you started with. But besides that, there's no. Hmm. 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 That's true. That's true. It will not converge. That is true. That is true. It will not converge actually. That is true. Because your theta A and theta B differential will always, the first estimate that you're going to draw will always be the same. That's correct. It won't converge. It will always run equally. So you'll have to sort of bias them by 1 degree at least to begin with. That's correct. That's true. Yes, that's correct. In this case, it won't happen, however. You can start with equal abundances because your reads are actually going to help you adjust their isoforms overall. But otherwise, that point is correct. Okay, so we have this distribution now, right? So we will try to assign them. We got these 5 reads, okay? We want to, what we want to do is we want to use this observed data to tell us what is the relative quantification of each of these isoforms. So just for like last experiment, I'm going to assume that each of these are equal abundant. So how does that happen? In the first step, which is the E step, since each of these are equally likely, which is 0.3, 0.33, and 0.33, I start by assigning each of them based on a very simple probability that if A is compatible with blue, green, and red, since each of them are equally abundant, A can be assigned 0.33 times to blue, green, or red, right? Similarly, B is red and blue. Both of them are 0.33 times. This will become clear once we do this. What will be the likely assignment of B? Both of them are equally likely, blue and green. So what should be the assignment? What will be the posterior? What will be the posterior? Posterior for, let's say, what will be the posterior probability of B going to blue? Hmm? What is it? 0.33 is the probability of seeing that read, divided by only 2 possibilities, right? B. B. A is easy because A is equally likely. B. Okay, let's see this in writing actually. Sorry, I don't have the. Okay, no, it's here, right? So I used to have a table actually, which is not there, but I'll add it anyway. So here, right, at one step, you started from 0.33. These are the 5 reads that you got. Now at the M step, you will have calculated each of these isoforms going to one or the other read, and you will recalculate, given this assignment, what does the relative probability of assignment to each of these isoforms look like. Okay, so let's try to do it here actually. So we have 3 reads, right? Red, blue, and green. What is the probability, what is the posterior of A being assigned to blue, green, or red? Okay, 0.33, fair enough. This is very simple to see. Okay, now about B. Yeah. Does everyone see how? Okay, C. D. That's correct. E. Red and green, right? Half 0. Okay, does everyone see this? So initially, how many, what was the relative abundance of red? 0.33. Now you will do the M step. At this step, you just re-estimate the relative abundance of R, B, and G, right? So what will this sum to? Overall, I have 1.33 isoforms of red. Sorry, 2.33, right? Okay. How about B? 1.33. How about this? 1 point. And what is the percentage? So this is at one round, after one round, these, I started from 5 reads, right? These are 5 reads. I started with an equal abundance that A, B, C are all equal. I get 2.3, 1.33, and 1.3. I'm going to re-estimate my theta R by saying 2.33. And what does that sum to? 5 approximately, which is 0.47. So 0.46 sums. Theta B, you can again calculate similarly, and theta G. So even though you started with equal abundance of them, after having observed that, you can now assign A more weightage based on the fact that you can assign red more weightage because most of your reads indeed are coming from the compatibility for red is the highest, right? So at the end of this cycle, you would, no, you're not. Well, yes, you are. Yes, you are. Yes. At this point, because that's what your compatibility class tells. Sorry, I assume that you're talking about the isoforms are always no. The reads are distributed based on their compatibility class, and there is no bias. At this step, there's no bias, right? But in the next cycle, when your theta A, theta B, and theta G have been updated, and if those are equal, that will sort of start to show here, essentially, right? That will get automatically accounted for, right? Because at this point, so we can do one more iteration. Let's do it. This is 0. We'll just copy the numbers from there, 0.27 and 0.27. So blue and green are currently equal now, right? Now in the next cycle, this becomes my prior 0.47, 0.27, 0.27, right? So this equal distribution that I had done for A earlier will no longer happen. It will now be 0.47, the normalized version of that, essentially. Right? So now you have gotten more weightage to the R. A very likely is, which makes intuitive sense if you think about it, because isoform A or isoform red is the most present at this step. So whenever you see a read, it's more likely that it came from this as compared to these two, which earlier was equal. So it will get adjusted for in the next cycle. Okay, does that make sense? Okay, you keep doing this, right? So you'll keep updating this again and again. That's what this particular tries to show. So in the next cycle, most of your stuff of A is actually coming from the red part, right? That's become half. And this read, which was Read C, which was equally assigned to blue and red, has also been encompassed again with the red one. And you can see why, because there's some differential that's coming from your prior exposure. Yeah. A is more probable from the red one, because the red one in my first update seems to have more promise because it has D, which is uniquely assigned to it. Right? So the abundance, the reason I'm able to assign A more probably to red is because red is more to begin with. So I'm biased because of the presence of D, which is specifically coming from from red, excuse me. So the probability of seeing, if I randomly sample molecules, right, I have higher chance of observing the red molecules. So I'm going to say that's what I'm doing there also, that I'm saying that initially I did not know anything, so A could have come from anything, but now I know red is very abundant, right? Right? It's this abundant, 0.55. Very likely A also came from red. I'm assigning probabilistic. I can say whatever I want to say because this is probabilistic, right? I'm not giving it a full identity there. It is helping you estimate the isoforms, right? Where there is no other compatibility class. In this case, there is no other compatible isoform to D. That is giving you the confidence that A is more abundant, right? Red is more abundant, excuse me. I keep saying A. This is red, which is more abundant. Because of this read, which is uniquely assignable, this is a small example, but think about it, that if you have a lot of reads which are only assignable to one single isoform, you will have more confidence that that particular isoform is more abundant as well. Because it's not everything is otherwise uniformly sequenced, right? So if particular isoform is more present, you'll have more reads coming from that isoform and no other isoform. Make sense? Not convinced? Ah. Shruti, yes. Hmm. Hmm. Fair enough. That's also a good point, right? So it's a longer version of that's fair. That's fair. That's fair. Yes. So in this case, that's fair because you have more isoforms, so more chances of originating from a particular isoform. Correct. That's correct. Good question. Translocation, you can, but hard, generally, not by usual methods. You will have to come back to this data, figure out what did not map, because it will run into, so just for everyone's context, translocation are these arrangements that happen when one part of this thing can get lifted from this isoform and get pasted somewhere else out in the wild. You cannot directly. You will have to come back and see what did not map and then try to see whether it maps anywhere in the genome. And that will tell you whether translocation happened or not. But by default, this will not help you find out what are translocations. It's doable, but requires engineering patch. Okay? Any other questions? Pretty accurate, actually. Yeah, exactly, right? This is one of those magic which works. And it works, yeah, even I was like, wow, this is crazy, right? Like, but in the sense that that's the beauty of probability, right? Like that's why there are so many exams. There are so many questions on probability because like the goal is not to sort of like not to pull you down, not to sort of tell you that like those questions by the way were very hard. So but they are hard for a reason because um, that once you go out, like you should be ready that things are not as easy in general, and that's true for me also, right? I know things are hard, so that's why the exams are hard by default. So you should not pull you down. The focus on probability for this class is also to give you that thinking that everything is actually very probabilistic, right? And there's no exact things. But when it works, it works. It works very beautifully, right? You're not actually breaking that read. You're not assigning it to one isoform. You're assigning it to all isoforms, but it is still accurate, right? The reason it works is because you're measuring so many molecules that it kind of averages out. So the law of large numbers, which we have not discovered, we have not discussed in this class, kicks in, and that's why things work. Okay, we are keeping the tradition. We have overshot, but I do want to actually I do want to finish the assignment, the hands-on. No, you're not close. Don't close. Not yet. Okay. So next class when we meet, we will talk about how do you actually analyze this data. Like how can we compare RNA sequencing? You have done it in cases. You have done it in controls. You are able to quantify now. Everyone should be able to quantify. You have been able to do this at the isoform level. And how do we compare that? If I got cancer, for example, then does it differ in my RNA? How does it differ between, let's say, a tissue where I did not have cancer? So if I take, let's say, my liver, if one part of the liver has already been detected with cancer, and if I compare this with something which is normal, what at the molecular level, what RNA molecules are differentially present? So this differential world you'll see a lot is that which molecules have made their way to certain genes now more, that means that they're making more of that particular kind of protein, which likely is something that might be causing you cancer, right? So a lot of what we're going to do in this part is associative. I do not know whether that molecule change happened and that's why I got cancer, or that I got cancer and that's why that molecule is now changed. You cannot never tell this unless you go in the lab and actually experiment what happened. But that becomes your entry point to figure out that likely what happened which caused the change between a cancer versus a normal patient. And I'm using example of cancer because it's in some sense unfortunately homogeneous, but also homogeneous in the sense of its presence. Like you'll have 1-2 degree connection who would have had it at some point. Nothing to be scared about in this modern world. It's curable mostly. And second, because it's complex, it's extremely complex, and you will see in some examples why it's so complex. It's a very, 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 very hard disease to crack overall. But what I want to do now is to go back and finish part of the assignment. And there's a very interesting part why I want to do this. Has anyone tried to finish the hands-on? No one. Okay, because this was mid-sem week. That's fine, but we need to do this. So do people have it ready? See lesser laptops. So what I will do, right, is maybe I will give you a gist of one second. So I will start my data from this part. So I will start my, of course, some steps you will do, right? So I will just quickly walk you because we will not have time to go over it again. I will just quickly tell you about what is it that I was doing, right? So hopefully you have understood Callisto now, right? Like Callisto is just a way to quantify at the isoform level, what does the counts look like? So we downloaded these counts data from the Geo website. This is what you're seeing here. It's nothing but each of these files look like the gene ID and the corresponding counts. Okay. Now, when you quantify this using Callisto, what you will see is the quantification is done at the what's called the transcriptome level, right? So at the isoform level, excuse me, 1 second. So I do have this version which is net. Probably put it up. So sorry, don't have that version here. But overall, so when you run the Callisto, you will see that you will get a TSV file, which is what I'm showing you here. So please go back and do it because you will have a lot of questions in the process. It will create an abundance.tsv file, which will have the isoforms as its columns and the second column will be the number of counts of that isoform. You will see that those are not whole integers because of this probabilistic method that we talked about, right? So each isoform red, green, blue, it's quantifying how many overall reads that it gets overall, and that is a quantitative number. That's a probabilistically assigned number, so that will be not whole numbers. In this step, what I'm doing is, while isoform level quantification is great, but my first pass to any analysis will be, I just want to see which genes are differentially expressed. So while I motivated all this class to tell you about what is the quantification difference at the isoform level, when I actually do the analysis, I will do this at the gene level. To do this at the gene level, what I will do is I will take each of these isoforms, red, blue, and green. If they all came from gene 1, I will just sum them up, right? So if this is 2.33, 0.46, and whatever, that number will be, count will be 5. So in this step, I am doing exactly that. I am taking the isoform level counts. I am reading what's called a T2G file. So T2G file is that this isoform 1 belongs to gene 1. This isoform 2 also belongs to gene 1, and maybe this isoform 3, which is red, also belongs to this gene 1, and so on. Yeah, sure. Nothing but this step, right? So at this step, I have my isoform R is 2.33 is the quantification, right? Isoform B is 1.33, 1.3. These will be non-whole numbers. Could not be whole numbers. These could be any floating point numbers. This is at the isoform level, but all these isoforms are coming from the same gene. Let me call it G prime. So in that step, what I'm highlighting right now, what I'm doing is, because there are a lot of isoforms, there are 100,000 plus isoforms, and I cannot deal with them right now. So to make my life simple, what I'm doing is I'm collapsing this at the gene level by essentially just summing these numbers up. So this will be like 5 overall. Okay, that's what this step tries to do. I don't have to do this, by the way, right? Because you've already downloaded counts, which, sorry, that's not what I wanted to open. You already have downloaded counts which are these gene to column counts, because that's what the geo record was about. I am creating this because I wanted to show you, and when you knit this notebook, you will see that what you quantified using Callisto is very similar to what they deposited. Even though they have not used Callisto, they've used a different way to map this data. So this step tries to show you that how does your comparison of what you quantified yourself using Callisto compares with what they quantified using their data. So this step just shows you that they are equivalent to each other. Okay. So that's what this says, that we are getting a correlation of 0.97, which is great. That whatever you are doing, you started from raw reads and not from their counts. Those are comparable to their raw counts overall. And then you get into this differential expression business. So this is what we will talk about next. So this has become one of those vignettes which we will keep with us for the rest of the session. And all of this will start to become clear when I talk about the normalization thing. And there are a lot of interesting things, by the way, with this data, that if you're interested in finding patterns and trying to decipher graphs, you will have a lot of fun with. So even if you don't run it, that's fine. We will do it again. Once we discuss some theory, we'll come back to it. So I'll let you know once we start this part. So far, what I expect you is you should have done Callisto quantification and been able to compare how does a raw read counts look like for with respect to what you downloaded from Geo. Okay. Okay, we will end it here, and next time when we meet, we'll talk about how to analyze these counts. Thank you. Below side. This one. Louder, louder, louder. Speak loud. So this is sample A, this is sample B. these are reads from sample A, these are reads from sample B. They are just differentially colored because I want to contrast them. They are all mapping to the same gene, right? And you can see that the numbers here is different, right? This has lesser reads, this has more reads. I wanted to use this to motivate that can I directly draw a conclusion that this gene X is more expressed in sample A as compared to sample B, or should I do some sort of normalization to draw that conclusion, which is what we'll do in the next class. No, so these are raw reads, so they're already mapping to the locations, right? So this is definitely mapping to here. So a lot of reads, right? So this entire gene X has like some whatever 10 reads or so on, which are already mapping here. And in this case, it's only 3 reads. This is sample A, sample B, case, control, cancer, normal sample. So my question is this happening because there is something biologically different between them, or is it happening because of certain other technical factors, which is what we will come back and discuss on Thursday. But they're already mapping, their reads are already mapping there. SNP, single nucleotide polymorphism. That's a good question. So whenever we do RNA-seq, we are very liberal in some sense. We usually will discount SNPs and we will consider this as part of your normal isoform. So even if you have SNPs, it will get mapped to the same gene. You can come back to it and figure out whether you should call that particular SNP out or not. But in most cases, you will just be able to map it as well. Yeah. Is that known? You're making a hypothetical example. Okay, fair enough. So RNA sequencing is only one step to answer this question, right? So, forgetting your name, Payal. So Payal's question is that if you have a disease which is coming because of, so I think we've run out of time, but just quickly, if you have a disease, right, which can happen because I have a mutation in my DNA somewhere here, and the normal should have been, let's say, a T, or maybe just simplification C, then how can I capture this using RNA sequencing data? That's kind of, or what will happen in this case, right? Because of this, what is happening is you get more copies, let's say, you get more copies of this RNA and you don't get copies of this RNA. So it depends where this SNP is located, first of all. Is it located in the transcriptional start site region, or is it located upstream of it? If it is located upstream, which is what is called the cis regulatory elements or the non-coding region of the genome, RNA sequencing will not tell you this because you cannot capture it, right? So the only other possibility is, okay, maybe it is located indeed in the protein coding region of the genome, which means you will be able to capture it. But when you use tools like this to align, it will not actually give you, it will not tell you that, hey, you have a SNP. You really need to go and find it yourself. So it's like a needle in the haystack lost. And RNA sequencing is not the most sort of precise technology to do this. You should go and do DNA sequencing to figure out whether you actually have a SNP there or not. So that's what is done usually in genotyping. So you can genotype these individuals to figure out what SNP they have overall. So you should have 2 assays. That's what becomes multi-omics. You have DNA sequencing data and you have RNA sequencing data. Because RNA sequencing data is good for doing functional studies, but it's not the most appropriate for calling mutations out. You can, in principle, you can. There are methods to do that, but that's not like as straightforward as it is with DNA sequencing. Okay, thank you.